Bismillahirrahmanirrahim. Hello everyone. I hope you are all doing well. I welcome you all in class of elementary number theory by David and Burton. My name is Azmat Ali. Our discussion is continue on properties of GCD. In today's lecture, I will discuss some very nice properties of GCD. Actually, these are the important questions available in the book of David and Burton in problems 2.4. But I am going to categorize all of these questions which are related to GCD as the properties of GCD. So the first and very important nice property which says if GCD of A and B is 1, that is A and B are relatively prime, then any integral power n of A and B has a GCD equal to 1. If A and B are relatively prime, mean to say their GCD is 1, then GCD of their sum and their product is also 1. And third one is actually the properties of associative properties of GCD of three integers A, B and C. This property says if you find GCD of three integers pairwise, like firstly you find GCD of A and B, and then again find the GCD of these two numbers AB with C, then the final GCD will be same as GCD of AC with B, GCD of BC with A. All these three GCDs are equal. So before going to start our discussion, I will revise some of the important facts that we have already discussed in our previous lecture. What is the definition of GCD? We say if we have two any non-zero integers A and B, then a positive integer D is called GCD of AB if it satisfies the following conditions. D must divide A, D divides B. The condition 2 is if C is any common divisor of A and B, then C must divide D and C will be less than or equal to D. The second fact that I will use several times in our lecture, and our today lecture might be a bit long. The second fact is, as C is a common divisor, C is in above definition here, C is a common divisor. And D, this is the greatest common divisor. Greatest common divisor. Always remember, C always divide D, that is the common divisor always divide greatest common divisor, and C is always less than or equal to D. For example, suppose 6 is a GCD of some numbers, then you can notice that here 3 divides 6. In this case 3 is less than 6. 6 is also divisible by 6. In this case 6 is equal to 6. So a common divisor is maybe equal to dividend and maybe less than or equal to dividend. That's why C is less than or equal to D. Both conditions may be hold. Now we move towards our discussion. The first property is actually question number 5. This is the question number 5 problem in problems 2.4. The question says, this is question number 5a. This question says for n greater than or equal to 1 and positive integers a and b, show that if GCD of AB is equal to 1, then GCD of A raised to power n, B raised to power n is equal to 1. I will prove this question by two ways. The first method is mathematical induction. To prove the result, we use induction. So according to mathematical induction, the first statement is result should be true for n is equal to 1. It is given that the statement is true for n is equal to 1. This is obvious. When you put here n is equal to 1, this becomes GCD of AB is equal to 1, and this is given. So result is clearly true by definition. Suppose that the statement is true for n is equal to k. That is, when you put n is equal to k here, then we have GCD of A raised to power k, B raised to power k, this is equal to 1. So this is our hypothesis step. Next we will show GCD of A raised to power k plus 1, B raised to power k plus 1, this is also equal to 1. So here I will use some previous result. If GCD of AB is equal to 1, then remember that GCD of A with any integral power of B and GCD of B with any integral power of A is always equal to 1. You can verify this result by a simple example. For example, if you find GCD of 5 and 3, clearly their GCD is 1. GCD means a greatest number that divide both of the numbers. This is only 1. Now if you increase power of one of them, for example, if you take power of 3, square of 3, this becomes GCD of 5 and 9. Again you can observe that the GCD of 5 and 9 is 1. So if you increase any integral power of A or B, in case when A and B are relatively prime, then this result hold for every integer k. Next, by using property 20a of section 2.2, that says if GCD of two number x and y is equal to 1 and GCD of two number x and z is equal to also equal to 1, then the GCD of x and y z, this is also equal to 1. Actually, what does this property say? This property says, if you notice, there are the only three integers in this property, x, y, z. One of them is common in both, that is x. So the common number will be remain same, and the second, and we multiply the second numbers, second numbers in both. This becomes yz. So the final result GCD of x and yz will be equal to 1. For example, GCD of 3 and 4 is equal to 1. Similarly, GCD of 3 and 5 is equal to 1. According to this property, GCD of 3 and product of the different number, that is 4 and 5, this becomes GCD of 3 and 20. This is equal to 1, and you can verify that this is true. GCD of 3 and 20 is always 1. So I will use this property like as here GCD of A and BK is equal to 1. This is true from here. And GCD of A raised to power k and B raised to power k is equal to 1. This is our inductive hypothesis. Now in these two GCD, B raised to power k is same. So we can multiply these two different numbers, A, K and A. So according to this property, we can write it as B raised to power k is same in both, and we multiply the two different numbers, A raised to power k and A. So this becomes A raised to power k into A, which is A raised to power k plus 1, and B raised to power k. So we have GCD of A raised to power k plus 1 and BK is equal to 1. Say this is double star. Again, as this star also hold for every integer k, so we can replace here k by k plus 1. This property hold for k, it means this will hold also for k plus 1. So GCD of AK plus 1 and B, this is also equal to 1. Say this is triple star. Again using problem 20a for double star and triple star. In double star, the same number is A raised to power k plus 1 here and here. The different numbers are b raised to power k and b. So we can multiply the different numbers. So finally this becomes GCD of a raised to power k plus 1, and by multiplying these two different numbers, this becomes b raised to power k plus 1. And this shows their GCD is equal to 1. That is required. So the statement is true for n is equal to k plus 1 whenever it is true for n is equal to k. Hence by induction statement is true for every positive integer. Next I am going to discuss its alternative method. In this method, it is given that GCD of AB is equal to 1. We suppose on the contrary, and we have to show that the GCD of these two numbers A and B is also equal to 1. But we suppose on the contrary that the GCD of these two numbers is equal to some positive integer D. As D is a positive integer, so I am taking here D greater than 1. On the contrary, at the end I will show that D cannot be greater than 1. And if we take D greater than 1, then GCD of AB is not equal to 1. Now, if some integer D is greater than 1, that divide both A raised to power n, B raised to power n. By definition of GCD, if D is the GCD, then D must divide A raised to power n, and D divides B raised to power n. We also know a result if every positive integer greater than 1 have a prime factor. For example, 2 has a prime factor 2, that divides 2. 3 has a prime factor 3, that divides 3. 4 has a prime factor 2, that divisible by 2. 6 has a 2 prime factor 3 and 2, both divide 6. So every positive integer that is greater than 1 has a prime factor. So if D is greater than 1, then clearly there is a prime factor for D. So then every prime P, then let P is a prime factor, that dividing D. Now if P divide D and further D divide A raised to power n, then by using the transitive property which says if A divide B and B divides C, this implies A divides C. In other words, if first number divides second number divides third number, then first number must divide the third number. So here if P divide D and D divide A raised to power n, it means P divide A raised to power n. Similarly, when P divide D and D further divide B raised to power n, then P divide B raised to power n. Now we have a result. If P divide A raised to power n and P is a prime number, this implies P must divide A without power. For example, if 2 divide 2 raised to power 3, this implies 2 must divide without power, that is 2 divide 2. Similarly, 5 divide 5 raised to power 3, this implies 5 divide 5. This property hold only for prime numbers. But if your number is not a prime, for example, 4 divide 2 raised to power 3, this is okay. But 4 does not divide 2 without power. So this result is only true for prime numbers. So here if P divide A raised to power n, then P divide A. Similarly, if P divide B raised to power n, this implies P divide B. It means P is a common divisor of A and B. If P is a common divisor of A and B, it means A and B has a GCD equal to P. But it contradicts with the fact that GCD of AB is equal to 1. Above, we have supposed that there is nothing common in A and B except 1. Their GCD is 1. But from here, we have shown that P is a common divisor of both A and B. This is a common factor of A and B. So this contradicts with our fact. Hence, no such P and therefore no such D greater than 1 exists. So GCD of A raised to power n is equal to 1. And this completes the proof. This is question number 5b. This question says, if A raised to power n divide B raised to power n, this implies that A divide B. If some power of A, integral power of A divide the same power of B, this implies A divide B. It is given that A raised to power n divided by B raised to power n. So by definition of divisibility, there exists an integer m such that we can write B raised to power n is equal to A raised to power n into m. We suppose that GCD of AB is equal to D. By definition, D must divide A. It means there exists some positive integer, some there is some integer R. We can write A is equal to RD. Similarly, D divide B here. So again, we have a integer S such that we can write B is equal to SD. And further, we suppose that R and S have a no common factor between them, mean to say their GCD is equal to 1. By part A of question number 5, which says that if the two numbers are relatively prime, mean to say their GCD is 1, then their power of same power has also GCD equal to 1. As here R and S has a GCD 1, so R raised to power n and S raised to power n also has GCD equal to 1. From question number 2, from here, what is the value of R? R is equal to A over D. Taking power n on both sides, this becomes A raised to power n, D raised to power n. Similarly, from here, S raised to power n is equal to B raised to power n, D raised to power n. Substituting the value of R raised to power n and S raised to power n in 4. This implies 4 implies A raised to power n, D raised to power n, B raised to power n, D raised to power n has a GCD equal to 1. Now from 1, B raised to power n is equal to A raised to power n into M. This is my 1. And from here, value of B raised to power n is equal to A raised to power n into M. So substitute this value of B raised to power n here. Next, as here R raised to power n equal to A raised to power n over D raised to power n. This is given by here. So we can convert A raised to power n over D raised to power n by equal to Rn, and similarly this can be written as R raised to power n into M. So we have R raised to power n and R raised to power n into M has a GCD equal to 1. We know a result which says if k is any positive integer, then GCD of Ka and Kb equal to k time GCD of AB. That is, we can take common k from here. So taking common R raised to power n, which is a positive integer here, we can write R raised to power n into GCD of 1m. GCD of 1 with any integer m is always equal to 1. So this is equal to 1. So this becomes R raised to power n into 1. R raised to power n into 1 equal to 1. And from here, by taking nth root, we have R is equal to 1. Substituting this value of R here in this relation, A is equal to RD. From here, our A is equal to RD. Okay. This implies A is equal to RD. Hence, D is equal to GCD of AB implies our D is equal to A. By substituting value of D is equal to A here. What does this show? This shows that A is the GCD of AB. It means A will divide both of the components. A will divide B as required. Next, question number 6, which is also a property of GCD. If A and B has a GCD equal to 1, then their product has GCD also equal to 1. To prove this, I will take C be a common divisor of A plus B and AB. At the end, we will show that C is equal to 1. We will show that C is the greatest common divisor and its value is 1. So, as C is the common divisor of A and B, so C will divide both of the numbers A plus B and C divides AB. Next, we will use a problem 20D of section 2.2 that says if GCD of AB is equal to 1 and C is the common divisor of the sum of two numbers A and B, then GCD of C with A and GCD of C with B both is equal to 1. Next I will use this result, C divide AB. Since C divide AB and GCD of A and C is equal to 1 from here, GCD of A is equal to 1, so by Euclid lemma, C divide B. What is the Euclid lemma? Euclid lemma says that if we have three integers A, B, C, such that the C divide the product of A and B, if the GCD of C with one of them, like here, GCD of A and C is equal to 1, then it must be that C divides the second number. You can verify this by a simple example. For example, 3 divides 5 into 6. Clearly, GCD of 3 and 5 is 1. GCD of 3 and 5 is 1. It must be that 3 must divide 6. And it is obvious, 3 divides 6. So by Euclid lemma, C divides B. Similarly, again, consider this expression C divide AB. Now use GCD of BC is equal to 1, because we have two result here. GCD of BC is also equal to 1. And GCD of BC is equal to 1. So again by Euclid lemma, C divide the second number A. It means C divide A as well as C divide B. It means C is a common divisor of AB. C is a common divisor of AB. It must be that a common divisor always divide greatest common divisor. So C divides greatest common divisor of AB. What is the greatest common divisor of AB? This is equal to 1. So C divides 1. Now as C is a positive integer that divides 1, there is the only one possibility, that C must be equal to 1. C divides 1 and C must be less than or equal to 1 here. So which number satisfies these two conditions? A positive integer that is less than or equal to 1 and must divides 1. There is only one positive integer, that is C is equal to 1. Next I have alternative proof of this question. We suppose that GCD of AB and A plus B and AB is equal to D. This implies D divide A plus B and D divides AB. To prove that D is equal to 1, we will show that D cannot have any prime factor, because 1 is the only positive integer that has no prime factor. Every number which is greater than 1 has always a prime factor. So to prove D is equal to 1, we will show there is no prime factor of D. We suppose on the contrary that there is a P which is a prime factor of D. Since P is a prime factor, so P must be divided D. Since P divides D and D divides A plus B and AB both, this implies P divides A plus B and AB. Again by using transitive property, which says if A divides B and B divides C, this implies A divides C. So from this property we can say that if P divides D and D divides A plus B, it means P divides A plus B. Similarly, when P divides D and D divides AB, then P divides AB. Now consider P divides AB. As P is a prime number which divides the product of these two numbers, so we have the following possibility: P divides A or P divides B. But it may be possible that P divides both of the numbers. So consider the first case. If P divides A, I can write A is equal to as A plus B minus B by adding and subtracting B. It is given that P divides A plus B. This implies P divides B. We know a result: if P divides the difference of two numbers and P also divides one of them, then P must divide the second number. This implies P is a prime factor of both A and B. Similarly, consider case number 2. If P divides B, now we show that P also divides A also in this case. So if P divides B, we can write by adding and subtracting B as A plus B minus A. As P divides A plus B, so P divides must the second number, P divides A. Again, P is a prime factor of both of A and B. So from both cases, P is a prime factor. A prime factor of D is a common prime factor of A and B, which contradict with the given fact that GCD of AB has no common factor other than 1. Hence, our assumption that P is a prime factor of D is wrong. So there does not exist any prime factor of D. This implies D is equal to 1 because only 1 is a prime positive integer that has no prime factor. And this completes the question. Next, we move towards the last question. Question number 11. Let A, B, and C be the integers, no two of which are 0. No two of which are 0 means suppose A is equal to 5, B is equal to 3, C may be 0. But this is valid case, but this is not valid. You say if A is equal to 5, B is equal to 0, C is equal to 0, this is invalid. So no two of which are 0, and D is the combined GCD of A, B, C. Show that GCD of A, B and C, GCD of A with GCD of B, C, GCD of B with GCD of A, C, all these three are equal and these are equal to D. Actually, this is the associative property of GCD. Here we will prove only the first part, and at the end we will say that by using the symmetry and arguments we can prove the remaining two. So we will prove that GCD of AB with C is equal to D. Suppose that the GCD of this component is equal to D1. So replace here D1, we have GCD of D1C. Say this GCD of these two numbers D1 and C is some positive integer D2. So we will show that this D2 is not different from D, that is they are same. So to prove this that they are same, we will show that D is less than or equal to D2 and vice versa. Mean to say, once we prove D is less than or equal to D2, and second we will show that D2 is less than or equal to D. So firstly consider the case how we will prove D2 is less than or equal to D. Here we will show that D2 is less than or equal to D and D2 is also divide D. In other words, D2 is a common divisor and D is the greatest common divisor of A, B and C. So our target is to show, we show that D2 is a common divisor of A, B and C. As D2 is a greatest common divisor of D1 and C. This is we defined here. D2 is the greatest common divisor of D1 and C. If D2 is the greatest common divisor of D1 and C, so by definition of greatest common divisor, D2 must divide both of the numbers D1 and C. So D2 divide D1 and D2 divide C. What's about D1? As D1 is GCD of A and B, so by definition, D1 must divide both of the component, D1 divide A and D1 divide B. By using transitive property of divisibility, which says if D2 divide D1 and further D1 divide A, it means D1 divide third number A. Similarly, D2 divide D1 and D1 divide B, it means D2 divide third number B. So D2 divide A, D2 divide B, and from here D2 divide C. It means D2 is a common divisor of A, B and C. As D is the greatest common divisor of A, B and C. We know a common divisor always divide greatest common divisor, and because common divisor is a divisor and greatest common divisor is a dividend. Greatest common divisor is a dividend and common divisor is a divisor. Divisor is always less than or equal to dividend. So D2 is less than or equal to D here. Now we show that D is less than or equal to D2. Now we show that D is a common divisor of D1 and C. Actually here we will show that D divide D2 and D is less than or equal to D2. As D2 involve the number D1 and C here, so that's why we will show that D is a common divisor of D1 and C. As D is a GCD of ABC, so by definition of GCD, D divide all of the number A, B, C. Consider the first two numbers A and B. As D divide A, D divide B, it means D is a common divisor of AB. D is a common divisor of A and B. If D is a common divisor of A and B, then D must divide the greatest common divisor of A and B. What is the greatest common divisor of A and B? This is D1. It means D divide D1. So D divide D1 and D divide C. From here, D divides C. So D divides D1 and D divides C. It means D is a common divisor of D1 and C. This implies D divide D2 and D is less than or equal to D2 because D is the divisor, D2 is a dividend. Divisor is always less than or equal to dividend because D2 is the greatest common divisor of D1 and C. Hence, from 1, both are equal. Hence, D is the GCD of A, B and C. By symmetry and by the same argument, we can show that they are all equal. And this completes our lecture. Inshallah, in the next lecture, we will start from the least common multiples. Because, Alhamdulillah, we have completed all of the questions which are related to properties of GCD given in the book of David M. Burton. I hope you have a clear understanding of today's lecture. Still you find any difficulty in concepts, you can message me, inshallah I will reply you. So see you in the next lecture. Take care. Allah Hafiz.